and deployment in affordable and clean energy space, especially for underserved sectors of Indian society. The center's efforts span clearly on the clean energy generation storage, energy efficiency and economy, end-use optimization, and allied socio-economic challenges, particularly in peri-urban and rural regions. The center is supported by the Principal Scientific Advisor Office of Government of India and CSR support from Honeywell Mouton Solutions India Foundation and Load Services India Private Limited. We have from the center the laboratory facilities, and these facilities have been extended to nearby regions of IIT Dharwad. So you are welcome to come to IIT Dharwad and make use of these facilities to generate new innovative solutions. Also, the center is providing upskilling, uh, and then one of the program we conducted last week, that was an upskilling on sustainable development and goals. That was an awareness program. And the next upskilling program is scheduled on 24th and 25th of November on the communication skills, and it is open to all. For these upskilling programs, we also provide the travel and subsistence allowances. So now I would like to introduce the guest speaker today before inviting him to begin the talk titled Energy Harvesting Trends and Applications. Dr. Pradeep is an associate professor and vice principal, academics and research at BLDEA's VP Dr. PG Halakatti College of Engineering and Technology, Vijayapur in Karnataka. He completed his PhD in the year 2017 from IIT Madras, Department of Applied Mechanics. Earlier, he has completed his MTech from Bagalkot Engineering College, Bagalkot, and BTech from Bijapur. His research interests are mainly focused on structural dynamics, energy harvesting, and IoT. He has published in leading international journals, presented his work at several conferences. Also, Dr. Pradeep holds a patent. He has professional membership with ISTE, Automatic Control and Dynamic Optimization Society, International Society of Nonlinear Dynamics, and Energy Harvesting Network from Southampton University in UK. He had secured funding for his research to establish this energy harvesting and IoT lab at his institute from VGST Government of Karnataka. His research work is also funded by the VTU research grants. I request Dr. Pradeep to please share the screen, which he has already done, and start his presentation. I request the audience to post questions in question and answer box or chat box, whichever is comfortable. Over to you, Professor Pradeep.
Sure. Thank you. Thank you, Dheeraj, for introduction. And
Thank you.
we have a lot of things from your Center of Excellence. Maybe we'll be making use of this in future. Thank you. Thanks to Global Center of Excellence in Affordable and Clean Energy, IIT Dharwad, for giving me this opportunity to share my research experience with you all. Today, I'll be just focusing on my research work or whatever we have done in our lab and previously what I have worked in my PhD research. That I'll be sharing with you. Today, I'll just focus on what this technology is about and where are its application and different challenges, and so what are the roads forward for us and how we can go beyond it. Mathematical part, I'll be just covering a bit of mathematical things, some just basic equations. Mainly, I'll be focusing on how we can take this for like what I'm studying today, startup. So it has a lot of application where we can start with a new product and come out as a startup. I'll be just going through my talk as here. Like I'll just start with the introduction. Like we'll see what actually is the big problem that we're looking out, and so how this technology can solve that particular problem. Then we focus on mechanism, how energy can be harvested. then what are the challenges and how those can be met and those can be overcome. And there are different applications of this dual application, like we can do multifunctional out of this energy harvesting as well as controlling. At the end, we'll cover summary and different applications. What is the market applicability of this one, commercial avenues. So those will focus on and where actual that research happening in different institutes within India and outside India, different societies we look into. So let us start with introduction. So introduction first. Let us start with what we are talking a lot about this Internet of Things. So how this evolution of internet has happened? So we all know, those who born in early 80s and 90s, we have passed over these stages. We were in the stage where getting telephone itself was an status, like a kind of status. We used to have telephone in one line, like in one colony, we used to have two or three telephones. But slowly it has picked up. We have started moving from telephone to mobile, and then SMS came into picture. That is what we came from. Our generation came from. That is pre-internet era. Then we entered into the internet era, where we used email, entertainment things, all those things which has internet connection, and we started communicating via email. So we can say digital communication was possible because of entry of internet. Then came the era of internet services, where we started purchasing, we started window shopping. So e-commerce, Amazon, all these things entered, and we started purchasing online. Then we started connecting with the people who are far distant for us, but still we started chatting and we started knowing the status. So we have like Facebook, Twitter, WhatsApp, LinkedIn. So for different platforms are there where we connected with people, that we can call it as Internet of People. Now we are in the era of Internet of Things, where we can connect our electronic devices and we can know the status of our machines, structures, building, or even human health. So all these things are made possible because of the internet, or by we call it as Internet of Things, connecting the things together by using the internet, so that we can track them and monitor them in real time. So this is how, like, we know a lot how IoT works. But our focus is not on the IoT, but powering this IoT. So there are different solutions are available that will be addressing. Just will go through those things in today's presentation. What current technological demands are there? Like, along with Internet of Things, and that Internet of Things has made possible to go for smart cities. So smart cities, we want everything to be connected, everything to be controlled in real time. So all the data we want to be in real time, processing time can be reduced. Even we want e-governance, we want smart energy, so we want smart metering, we want smart transportation. So these all things can be made possible by use of Internet of Things. So how Internet of Things, like what basically Internet of Things is, like we will be connecting lot of the things around us using internet, and we can collect this data in physical world data. We can collect it and we can process them. Then we can use present AI and take the decision, and we can control the things. But what is the problem that we are addressing now? Like, what the problem? Like, we will be needing lakhs of sensors, and this lack of sensors need to be powered. But with advent of technology, size of sensor has been reduced, but it is not so with the case of batteries. Now we call it as wireless sensor networks. So they are self-organizing, they are pervasive, they are small in size. The only thing left is that should be addressed is whether they are self-powered or not. The answer is yes, they are self-powered, but how? They are self-powered by means of battery. But that is not proving to be sustainable. So there are different things which need to be addressed. So we'll address one of the solution. It may be possible in future. We can use as alternate to the battery, or we can use to enhance the battery performance as well as life, this energy harvesting technology. So this is how energy harvesting technology works. We have a lot of ambient sources surrounding us. It may be mechanical, it may be thermal, solar, or radio frequency. These ambient sources can be converted into useful electrical energy via some generators. We'll be looking out on these generators. What are the different types of generators are available? What are their advantages? How to come over their limitations? So energy storage, there comes some electrical major thing. It comes electrical. We'll not be focusing on that, but that is a major challenge that should be integrated if you want to come out with a complete product. So once stored, then it can be either used for some electronic devices or it can be used to charge up the battery. It has a lot of applications. The output we will discuss, like what is the amount of output. Usually, amount of output we can expect here is in terms of milliwatts. So which has application in low power sensors. It has other advantages also like health concern. Batteries are usually made up of lithium, and every 5 years or 6 years we need to replace batteries, and that will produce a lot of e-waste. And it can also reduce maintenance. So like in case of animal tracking, we want tracking of animals. Like some people want to know this position of their pet animals, so they're using collars. So those can be powered by kinetic energy harvesting. So which replaces battery, and it doesn't require a frequent replacement of those batteries, especially in case if you want to track the wild animals. Accessibility, some places like we have bridges or offshore structures. So where it's very difficult to reach there. So where there's a problem of accessibility, we can have this kind of system there. So if you come to application, there are a lot of applications like maybe defense, biomedical, structural health monitoring. There are various applications available that we'll see at the end of this presentation. Okay, one more comparison, like how it is compared with battery. So we can see battery performance initially when you battery is new, so we can expect high power from that, and as days passes, it start discharging. And normal our AA size batteries after 1 year, the energy left in that is almost zero. But energy harvesting, so the anyhow the amount of available energy is low, but it is continuous. So we can harvest energy and again supply, harvest energy and supply. It doesn't go to zero, but it won't go to zero. But we can again recharge them and we can harvest from them again. It keeps like it's a cycle, continuous cycle. We cannot say infinite, but it is for the longer time compared to battery. I am talking about energy harvesting, but for most of us, energy harvesting also is not a new thing. But we know all this energy generation, thermal, hydropower, solar, all those things. But the taxonomy I'm talking about, and what is the level of energy that we are getting from this, and where exactly the application. So we already have seen this huge wind towers, hydraulic energy generation, or maybe solar, big solar panels. So we are producing there. We can expect power in terms of mega scale, in terms of megawatts. Also, we have seen generators. So for compact usage, it has an scale of in terms of watts. But at present, we are focusing on micro scale power. So whatever in today's presentation, if I say energy, it will be in terms of from nanowatt to milliwatts, maximum milliwatts. So that's about like this has made miniaturization is possible, and this can be applicable for the IoT. What are the different ambient sources and what are different generations? Like how we can convert that ambient into electrical energy. So these are some of them, but we have many of the energy harvesting generators. So the basic one, we all know this Faraday's law, all those things, electromagnetic energy harvesting, which uses waste mechanical energy, or we can say generator, which converts, like we know that standard, copper coil and magnet arrangement. So that is due to the magnetic field. So we can harvest energy from mechanical vibration or mechanical motion and convert that into electrical energy, and we can store it. So second one is piezoelectric energy harvesting. It is specifically, we can say it as smart material. Piezoelectric material is a smart material. So here energy can be harvested because of the strain. So we know that piezoelectric material which has a particular property, like if you give the mechanical input, it produces electrical output, and reverse also is possible. So we'll be using one of that reverse property, that is mechanical to electrical, and we can either store it or use it for the some microsensors or MEMS devices. Also, we have electrostatic, where we'll be using change in capacitors. This also is one of the options. So next we have thermoelectric. From thermal, we can whenever we have a temperature difference between two nodes. So in particular, we have N type and P type thermopiles. So because of temperature difference, voltage will be generated. So that can be used. This has good applications in case of automotive exhaust, human body energy harvesting. Also, we are using, we know this solar energy harvesting, but as I said, we'll be talking anything in terms of, that will be in terms of small scale, so milliwatt. So we like there are some PV cell technologies there now. We are coming out with thin cells. Uh, so PV cells like these can be made as variable solar energy harvesters. We can harvest energy with variables. So these are different generators from which we can convert ambient energy into electric energy. Apart from this, there are various things are there nowadays. Uh, Triboelectric energy harvester is coming handy for variable sensors. There are a lot of things, but these are the major. We'll be discussing on one or two of these things. Energy level, as we have seen, like there are different sources: vibration, thermal, and photovoltaic. Sort of these, how much energy we can expect, and then we'll see what are the challenges and how much is the efficiency of these all generators. So if you go for photovoltaic or solar, we can harvest energy up to 10 milliwatt per centimeter square. From vibration, it is starting from 4 ultrawatt to 100 megawatt. Or nowadays, with improved harvesters, we can reach up to milliwatt scale also. From thermal, it is in milliwatt, 1 to 10 milliwatt. Also from radio frequency, it is very low, but so in some cases we can use these things where only available source is radio frequency. It is in terms of, we can say, ultrawatt or up to some microwatt level. So we cannot say which one is good or which one is bad. It depends on where we are using it and what is the situation and what are the different what is the type of ambient source available with us. So next we'll go to the mechanism. So what are different conversion mechanism? So let us start with thermoelectric energy harvesting. So we know, like when we have PN junction and we have heat source and heat sinks, there will be temperature difference. So we have all studied the Seebeck coefficient. So more the temperature difference, more with the potential difference. That potential difference can be used to supply for some of the MEMS sensors. So this plot shows how the difference in temperature can influence the power output. Also, there are various different plots of efficiency and voltage. So in this case, it mainly works on Seebeck coefficient, Seebeck effect, or we know Peltier effect. Based on that, whenever there is a temperature difference available, so we can use this kind of technology. So one of our recent work, we took the commercial TEG, we can say, thermoelectric generator. So, we compared, like usually the normal shape is rectangular or square. So if we use different shapes of these legs, what will happen? That study was conducted and recently we published that in EPJST. And also we try to change the leg the shapes. We consider single leg and how it can change the performance of the TEG. Usually, square was the most optimal, but even in some cases, circular and rectangular are found to be better from the efficiency point of view. Commercial level, these TEGs are made up of bismuth telluride. It has some limitation. It cannot go work beyond temperature 200 degrees Celsius or up to maximum 300 degrees Celsius. If you want to go beyond this temperature, we need to use different specific materials. So coming on to the vibration, we have seen these different vibration harvesters generators, how it works. Like we have ambient source as vibration. From here, we can harvest, convert the energy with these different generators. Then we can either store it or send it to the device. So what is the challenge? What's most important here? Like just we are talking from mechanical, just to have the glimpse how it works. So this is our harvester. It may be whatever. It may be thermal, whatever vibration, whatever. Once harvested, then it should go through the rectifier circuit to convert into DC, and then so these things are important. V in and V out. The inputs and output, we want to maintain the V out to be constant. V out has to be maintained at the constant level, so that it should not be like we don't want to our microcontroller sensors to be affected due to the fluctuation of voltage. So this charge management is very important in nowadays, because some of the times, most of the times from ambient source, we have the intermittent energy supply. To maintain that, we need to have a good charge management. So this neural network DNA and AI comes handy to making this charge management, so that we can overcome the intermittent power problems. So from here, if you can maintain V out constant, then we are successful. We can successfully send that power to the microcontroller, through which we can power up the sensors. And again, then this data can be sent to the main workstation. So already we have seen how piezoelectric works, and most of the time we have come across these things. So piezoelectric, electromagnetic, and this is variable capacitor, electrostatic harvester. So electromagnetic, we know this standard due to that is Faraday's effect. Whenever a magnet moves between coil or copper coil, so EMF is generated due to the relative motion. Based on that, so energy can be harvested, and these are the basic electromechanical equations. So we have mechanical as well as electrical system here. So we'll be always facing these electromechanical equations whenever it comes to the energy harvesting. It is, we can say this as interdisciplinary work. So once you want to go for application, real-time application of this, you need basic electrical knowledge, and to some extent we need expert electrical domain. It's good for and collaborative work. So these are the equation. The first equation is mechanical part. We know so this inertial term, damping term, and stiffness term. So this is the mechanical equation. And second, so these are the coupling terms from electrical to mechanical, and this is our acceleration due to acceleration, that are base excitation we can say, and these are the electrical terms. And this omega c comes from the mechanical equation. So these two are coupled together. From this, we can see how this voltage can be generated. So the NB, these are the electrical terms. dx by dt is the velocity, mechanical and electrical terms. We can harvest energy from this electromechanical or electromagnetic energy harvesting. Similarly, piezoelectric, as we discussed, as we know, this is a smart material. Here we'll be using effect when mechanical is input and we are expecting electrical output, and is based on the strain. So again, it has electrical mechanical equation remains almost same, and this is electrical part of the equation for the piezoelectric. Similarly, variable capacitance are electrostatic energy harvesting. So this is electrical part of equation. So we have other things also, like triboelectric also is one of the main vibration energy harvester, or if not vibration, which is based on the friction, we can generate the energy harvesting. We can generate the useful electric energy. These are different harvesters for vibration based energy harvesters, we can say. So I have listed some of the advantages and disadvantages. It's taken from Yang et al. In 2007. You can refer these. So as we discussed, we cannot say which is better and which is. It again depends on where we are and how we can use it. So already we know electromagnetic and electrostatic, they are not smart. but piezoelectric is a smart. So miniaturization, like usually in case of MEMS, we prefer piezoelectric. Whenever you have more space, because electromagnetic need a lot of space. It is usually displacement based, but only thing it doesn't require any smart material. So cost point of view, electromagnetic is best, but if you go for the space restrictions, then piezoelectric will be the better one. Okay, this is a conventional harvester. Our first harvester, we can see it way back in 1996. So we had a first model of energy harvesting, where they used electromagnetic energy harvester. They produce in a small amount of energy. So we say it as linear energy harvester. So we all know how this linear vibration spring mass system works. You can see this small simulation. So there is a forcing frequency as well as natural frequency of the system. So we know resonance condition. So whenever forcing frequency matches with the natural frequency of the system, we will get the highest amplitude. And same we can expect from the energy curve also. So we can expect maximum power only at the condition of resonance. But apart from that, what happens? We can see a huge drop of the energy harvested. So that is one of the limitation, like major limitation of this. So it can harvest maximum power only at the resonance. Apart from that, there is a huge drop. So there is a problem with band. The frequency band is very limited. The problem or the challenge is to increase this frequency band. Whenever you design this harvester, and we have, like, if this is a bridge, if you take this as a bridge, source as a bridge, and we design harvester for a particular frequency, and if this bridge frequency and harvester frequency doesn't match, so there is no resonance, and we cannot expect energy to be harvested from this device when connected to the bridge. So in order to overcome that, we need to go for the design of broadband energy harvesters. There are various methods through which we can harvest maximum energy at a broader frequency that you will see. So from our discussion, what we come out with different challenges. So there are different challenges. One is conventional energy harvester has single frequency power generation, and also there is absence of low frequency devices. So why we want low frequency devices? Because majorly we are focusing on the structural energy harvesting structures. So if you take mechanical machines, they are high frequency machines. They vibrate at high frequency. Usually these structures like buildings, bridges, they are treated. They comes under the category of low frequency. Low frequency in the sense less than 10 hertz. So we need to design design harvesters which can operate at the low frequency, and also which can operate beyond the resonance also. So this explains the absence of general application of this particular energy harvesting technology. Next, going on to the band enhancement, that is one of the solutions that we need from the existing solution. So there are various ways through which we can enhance the band. So one is by using multiple harvesters, or we can say multi-mode also. Multi-mode or array of harvesters. Second, we can go for the non-linear harvesters. We'll see what exactly is non-linear harvesters here and how it works. And third part, we can go from the advanced electronics network. But today we'll be limiting our discussion to only this mechanical part, though electrical part is very important from here also. So we can use different circuits, SSH and all those circuits to enhance the energy harvesting band also. Tuning also can be done using the electronic circuit. Let us see one by one if you go for multiple or multi-mode harvesters. So you have seen previously single harvesters, it can harvest maximum power at the resonance. Okay, what we can do is we'll take multiple harvesters, but instead of taking similar harvesters, we'll have dissimilarities, or we can say mistuning to be introduced. So these harvesters have different length. Then this has different natural frequency. This will be having different natural frequency. All of them have the different natural frequency. and resonance will occur at different frequency. So that, like, from first one we can harvest maximum power here, second one we can harvest here. Such in such way you can have n harvesters, and at different points we can harvest peak powers. So in that way we are covering this we can say overall power output, and we can cover this larger frequency band by using the number of harvesters with different dimensions. There is one more possibility. Instead of changing length, we can also change the masses. We'll be using n masses here to generate enough inertia. We can change the masses at the end of the beams. So this also will result in the same output. So there are different like fabricated, like using some etching technology or maybe 3D printing, different multiple harvesters. This is from University of Brescia, from Barcelona, and these are different. Like you can this is in circular arrangement, and this is in different E shape, different shapes on single. It's of size of PCB. They're of the size of PCB, or even some of the circular tube type harvesters. They have array of coils here. You can see these are the different coils, and magnets will be there inside. This is electromagnetic harvesting. We can nowadays metamaterial is a trending word, and a new material we can say. So we'll discuss about metamaterials also. So these are the different ways by which we can introduce multiple harvesters. So by which we can enhance the bandwidth of the harvester. But this also has a limitation, because if you want to go for multiple harvesters, so you have to compromise with the space. You are getting broadband energy, but the space limitation has to be looked into. Either like now, if you consider multi-mode, it's not a multiple, it is multi-mode now. So we know that any structure, it has multiple modes. Though the fundamental frequencies are fundamental mode, first mode is dominant, but even though second and third mode, from that second third mode also we can harvest energy. So it is more clear from this point. Like you can see, at first frequency you can harvest maximum power. Second, it's little bit lesser, but with parametric adjustment we can bring these peaks nearby. But so it's intermittent band, we can say here. It's not a continuous band. In between, we cannot harvest energy here. We can harvest energy when we have at 50 hertz and at 370 hertz. There is a gap, but still at 2 points we are harvesting energy, which is better compared to that of single harvester. So one more option what we have is this is from Karthik and others. So we can have piezoelectric and along with the electromagnetic, so that we can take both advantages of both. So here piezoelectric gives more voltage output, whereas electromagnetic gives more current output. So those both advantages can be clubbed here, and we can get added advantage here. So these are all multiple and multi-mode. So this has limitation of space. So we worked on something like coupled harvester. Like this is our work. What we did is we had electromagnetic, this kind of pendulum, and they are connected by the mechanical spring. With this, we try to optimize or minimize the number of harvesters without compromising the bandwidth or power harvested, magnitude of the power harvested. We studied 3 cases here. One is completely uncoupled, that means no springs available here. Second is coupled but not grounded, that means only these coupling between pendulum is possible and that available, but coupling with source or base is absent. So these two springs were absent. That is case 2. Case 2 only these two, and case 3 we have all the springs available. So if you compare the results, so for easiest, like we are just comparing first and third, that is without and with all the springs present. We can say from the frequency ratio band, there is case 3, there is saturation. Case 1, we can have the highest power. So you have selected a particular value of the coupling. Okay. We can see there is a saturation point. it, like if you keep on increasing the number of harvester, it always doesn't mean that it will always increase the maximum power or total power. There is a situation where it reaches the saturation. So again here we found coupling will give better frequency band than, rather than without uncoupled harvesters. So that experimentally we validated. These are some of the experimental results we can see here. So this is just uncoupled pendulums. Though there is a shift in frequency, and from uncoupled pendulums we are able to harvest only within this frequency zone or frequency band. If you introduce coupling, so there is a huge increment of the band. Yeah. So one more thing that I just missed. So these pendulums are of not same size. So they'll be having different sizes or different lengths. We call it as mistuning. Similarly, for three pendulums also we get fairly good results from experimental as well as numerical. So this is with the three pendulums. Next, coming on to the second option, non-linear harvesters. Like we have seen from previous that multiple harvesters is not always good solution if you have the space restriction. But can we enhance this bandwidth using a single harvester? So then the answer is yes, provided we'll go for the non-linear harvester. So this we know standard curve for linear and non-linear stiffnesses. Okay. F versus X, we can see this is a normal linear and this is for non-linear. So this is a potential well we can see. We have two wells here. If our harvester can travel between these two wells, then we can say the band has increased, also the output can be more. So we'll see one of the simulation here. So what is changed mathematically here? Previously we had mass, damping and stiffness only, those terms. So now along with stiffness, so this Kx term, we have non-linear stiffness here. That is cubic stiffness. X into x square is cubic. So this is a cubic behavior here, non-linear cubic behavior. We are introducing cubic stiffness here. So based on the sign of this, whether it is positive or negative, we can expect either softening or hardening effect. So here it is clear for us. If you go for linear, this is what happens. We can have the maximum power only at the resonance. If you go for non-linear with softening effect, so we can tune or we can reduce the operating frequency, and we can have for the larger band the peak power arrest for the larger frequency band. And same thing can happen if you change the non-linearity to the hardening type. So this is most famous, we can say, Duffing oscillator. A simple, like if you take simple cantilever beam and put two magnets here, and this has to be piezoelectric magnetic beam. Then this beam tries to start oscillating between these two magnets. So based on the polarity, either it is attractive or repulsive. So based on that, softening or hardening will be decided. Similarly, we can say levitating harvester. So there are harvester at the top and bottom of the tube, and this is the middle harvester, which is in repulsive arrangement with both the harvester. So this will be in a levitating mode. And also we can place external magnets to enhance the bandwidth. Bistability also can be achieved without magnets also. This is from Friswell and others in 2011. So this is using the buckling. If you can increase the mass beyond the critical mass, so you can see either this beam can buckle to the right or left. So it can oscillate at the right section or oscillate at the left section only, or it can transmit between right and left. Whenever it transmits between these two positions, then we can expect maximum power and maximum bandwidth obtained from that particular harvester. Okay, for more clarity, so this is what I was talking about, a Duffing oscillator. This we did it in IIT Madras Vibration Control and Energy Harvesting Lab. So a normal beam and pair of attached here and two base magnets. You can see this is oscillating between these two magnets. So we can say this is potential well number one, potential well number two. Either it can oscillate here only, or it can oscillate here, or it can has a change this stability point from here to here. Between two stable points, it can oscillate. This is standard duffing oscillator. If you can attach a piezo material here, you can harvest energy. This is one proposed by Inman way back in 2009. So what has happened here, we can see, okay, from voltage point of view. Okay, so piezomagnetome means it is non-linear harvester and piezoelectric is a normal linear harvester. Piezoelectric, you can see, it has highest power at the resonance. This is, you can see here, piezoelectric is outperforming the piezomagnetic. But whereas for all other frequencies, magnetoelastic harvester is outperforming the piezoelectric. It has a good frequency bandwidth compared to the piezoelectric. Only at the resonance, piezoelectric is good. So therefore, non-linear harvester can harvest maximum energy over the broader frequency. And there are also like then researchers started thinking, if we are using non-linear harvester, why not use multiple non-linear harvesters? Why only one? There are like multiple non-linear harvesters. We can see there's a magnetic interaction between these two, but three PZT is used here. That means three harvesters with non-linearity. So they have seen huge increment in the bandwidth, and this is kind of co-bistable harvester proposed by Joe in 2015. So based on this, we proposed one more system which was published in 2017 in Applied Physics letter. We considered, okay, this is magnetic coupling, these two are the magnet, along with mechanical coupling. Previously, we checked with what happens if there is a mechanical or spring coupling. And now we thought, okay, along with mechanical, if magnetic coupling also is present, so what will happen? Okay. So this is experimental arrangement. So these are the coils we can say, and this is magnet at the end of the pendulum. These are pendulum system. So these are the springs. Okay. So this is MCH. Capital MCH is magnetic coupling up down, and IH is independent harvesters. So magnetically coupled harvesters have shown increment of 150% of bandwidth compared to independent harvester, for especially for the pendulum number 2. So again, it depends on the mistuning. Pendulum number 2 is low frequency harvester. That's what it is getting advantage of the coupling. Similarly here, we can see increase in the bandwidth. At power of 70 microwatt, you can see a bandwidth enhancement. So this is for the independent, and this is for the coupled, magnetically coupled. This is for pendulum 2, this is for pendulum 1. So we can see that pendulum 2 has better performance compared to pendulum 1. Pendulum 1 compared to linear or uncoupled linear harvester, the output has reduced. Maximum power is less, and also bandwidth also is not that much. It's almost same. But whereas pendulum 2, so there is both increment of both in terms of magnitude as well as bandwidth. So this is because of energy transfer from pendulum 1 to pendulum 2, which is low frequency harvester. We also compared results with MMCF, that is magneto-mechanical harvester. Okay. See here, magneto-mechanical harvester and just mechanical harvester. So this blue one is magneto-mechanical harvester, which has a better power output as well as bandwidth. So previously, various people, they just tried with magnetic coupling, and they tried with just mechanical coupling. So we thought, what happens if we join together? So combination of both magnetic and mechanical proved to be better, and it was giving better output compared to both of them individually. If you see the dynamics, you can see passive periodic root to cables here. So if you change the frequency at particular coupling value, or we can say magnetic coupling value, you can see initially it is in linear zone and it enters into the chaotic zone. and this entrance of into chaotic zone is the through the quasi-periodic. We can see linear quasi-periodicity, and then it is entering to the chaotic. So this is where, like in chaotic only, you can see a lot of displacement is happening, like high displacement chaotic oscillations. This is the zone, chaotic zone. This is the zone where we can get the maximum displacement, or in other words, we can say maximum power. This is the range where we can harvest the maximum energy. No, like previously we talked about like one of the pendulum is producing better power than second pendulum. Then we start like in the recent paper in AAP Advances. This is a work along with Glasgow University and Lublin University, Poland, which said like why to go harvest from both the pendulums. Like in case of pendulums or harvesters, there is a lot of investment. Like we need to have a lot of parts there, harvest the energy, and if you are getting very low power from one of the pendulum, so invest compared to investment, the power output is less. Then it's better to avoid that harvester. We give a different range. Okay. Zone 1, Zone 2, and Zone 3. Okay. In this Zone 1, what we observed, anyhow, total is always more from, it is combination of pendulum 1 and pendulum 2. But in Zone 1, you can see that pendulum 1 is dominating and it starts reversal in Zone 2. So pendulum 2 starts dominating pendulum 1, and it has almost similar frequency band as that is produced from the total. So at this point, in this zone, so it's better that just go with the pendulum 2, harvesting only from the pendulum 2, such that we can reduce the usage of materials. In that order, we can reduce the cost of the harvester. Also, we can reduce the friction. Like if you're using harvesting from both the pendulums, there is an effect of friction due to the energy conversion. So that can be reduced, and even we have seen that this output is better than the existing one. It is almost equal to the total. Okay. So this will increase our performance. Like we can classify different zones. If a designer wants to work in particular zone, and he can decide whether to harvest from single harvester or both the harvesters. Based on that, he can take decision and he can optimize the material as well as cost. Along with that, what we found out that during that we have seen that there is a chaotic zone. During that chaotic zone, if you give some initial conditions, so previously it was without initial conditions. Initial conditions has also increased the performance of the harvester. You can see this is without any initial condition. Once you apply the initial condition, you can see jump in the current output. So here it's clearly visible. So with introduction of initial condition, okay, introducing this initial condition is not that easy, but then again you have to go for some control technique here. So that can be discussed in another platform. But so if you introduce initial condition, the enhancement in the performance can be observed. So these are the different basin of attraction where, so this is the zone. These are the zone of initial condition, a blue color, where you can expect better performance of the harvester. If you give this set of initial conditions, angular displacement and velocity, we can expect more power. So next, coming on to some of the dual functionality, we can say, so this is a standard building, and we are trying to control vibration of this building through this isolator. Or secondary absorber. We can say this as absorber. Dynamic vibration absorber. We can see this because of this absorber. So this is controlled in better way. Okay. So along with this, can we harvest energy? So this is the work by Ali and others in 2012. So this is primary system and this is secondary system. This secondary system mainly designed to control the vibration of primary system. Along with that, they try to harvest energy from the secondary system. So this energy can be used in rare cases, like a structure is under earthquake. During earthquake, we cannot expect conventional power to be there. then it's very difficult to collect the data of that earthquake. So then a secondary system can harvest energy from that earthquake vibration, and the data can be made available of that earthquake data, like data of the structure during the earthquake can be expected. So they found that it's not only harvest the power, it also controls the vibration of the primary system. It can reduce by measurable amount of vibration of the primary system. So this is vibration of primary system, and this is the normal power energy harvested from the secondary system. So we can do both, but there is a catch here. But we need to optimize one. Like if we want more energy to be harvested, what we want is more vibration of the secondary system, or in turn vibration of the primary system. So there should be an optimization between amount of energy harvested and amount of control of primary system amplitude. So many people, they have worked on different algorithms to optimize these two, vibration as well as energy harvested. So we did similar kind of work with pendulum oscillator, and we found that a structure, building structure, can be controlled. Okay, so we can have a compromise between uh, energy harvesting as well as control of this primary system. From this energy harvesting, if we can change the coil properties, we can increase the damping of primary system, and we can still control, we can still reduce the amplitude of the primary system. Okay, this is work from IIT. I think it is work from Rudra Pratap, Professor Rudra Pratap. So they, so like we started, like previously we talked about multiple harvesters. Now they came out with the idea of multiple absorbers with harvesters. This is primary system, and this is secondary system. So now primary system has multiple absorbers. So because of this, multiple band gaps of this primary system has been introduced. That means at multiple frequencies, you can reduce the amplitude of this primary system, as well as we can harvest the power at multiple frequencies. They are clearly given one absorber and three absorber system here. So it has highest band gap, like between from this point to this point. So the amplitude of primary system is 0, whereas for only one absorber, that band gap is very limited. So we also tried with different system in 2019. This is the work with University College Dublin. So we tried to couple these secondary system, and we observed it's not that much advantageous, but still has some effect on the amplitude of primary system and band of the harvested. Okay, now the interesting thing, like I'm not sure, but most of us were hearing about something called as metamaterials or metastructures. So we can say these are unnatural materials. We already know what is composite materials. So we are mixing two different materials, and we are making a material. We call them as composite materials. But here, it's not. We are not mixing different two different materials. So you are just mixing. We are making use of the periodicity. So we are engineering those materials to get the unnatural properties from that material. Like we know, or we all know Poisson's ratio, or we know stiffness. So we know only positive stiffness. Is it possible to get the negative stiffness? So answer is yes. That is only through the metamaterials. So we can obtain different geometric properties. That is only through the change in the geometry. We are not changing the composition, but we are just changing the geometry. So simple example, if you take, so consider this plate. So these are different holes, but holes are not circular; they are elliptical. So only a simple change. So what changes that this bigger hole has the major axis along x horizontal direction. Smaller hole, they have major axis along the y axis. If you compress it, usually what happens if you compress it with one direction, it has to increase, second direction it has to decrease. But that effect can be reversed by aligning these holes in different directions. A simple example, nowadays we are seeing some commercial ad like origami materials, or we played, all of us, we played with papers. We made paper boards, we made paper planes. So we didn't use anything, we didn't stick, we didn't welded anything there. We folded paper in different manner, and it was able to become stiff, and it was able to fly. So it was able to hold also. We just take a paper and here. So this is just simple paper. It cannot stay in horizontal position. Like if you make some folds or make this, we were just adding stiffener, and we made this same structure without adding anything. Stiff one, and it is capable of holding load also. So this is what beauty of metamaterial is. Like a lot of people working on this metamaterials. This metamaterial, the original word came from the Japan. They have different, more than 10,000 varieties or different patterns in these metamaterials. You can check those in later. But this can also be used in energy harvesting. Instead of going for single absorber, we can go for multiple mass in mass system, or different inertial mass system, inertial absorbers, those things. So instead of having single band, we can have multiple bands here. So this can introduce multiple bands along with these meta structures for. Usually in vibration, meta structures are used for the vibration mitigation. So along with mitigation, researchers also have explored possibility of energy harvesting. They have seen improvement in both mitigation as well as energy harvesting. So this is a recent paper in EPJ where we explored non-linear absorbers with metastructures. We have multiple absorbers here, 1, 2, 3. We can have n number of absorbers, and this is the bigger mass is the primary mass. So I think next slide we'll see how exactly in physical world it looks like. Okay, this is actual harvester system. This is from my previous lab in IIT Madras. Home energy harvesting. This is one of the hybrid energy harvesters. This you can see clearly. This is MHD, and you can see LED is glowing because of the harvest technology. This is hybrid system, electromagnetic and piezoelectric. In real-time application, we made a simple bridge kind of system here, and this bridge is subjected to vibration. So that vibration is transmitted to the harvester system and sufficient. This, and that energy is supplied to the sensor. So we use temperature sensor, wireless sensor, and we are able to acquire the data from that temperature sensor. So this harvester was better enough to power up the temperature sensor. We also checked this system in moving bus. So in vehicle location also it has harvested good amount of energy, and that was supplied to the sensor. Okay, I was talking about metamaterials or metastructure. So this is kind of metastructure. We can see this is our primary system, and we introduced absorbers, multiple absorbers here with non-linearity. It can be linear or non-linear. So this makes a metastructure. This is kind of metastructure. You can see difference between these two with and without absorbers. You can see a lot of vibration of the primary system, whereas here that has been reduced to zero due to the introduction of this secondary system. So this is our lab that Brain is making. Okay, now coming out to the market and products, there is a lot of market potential for this energy harvesting, like not directly as energy harvester, but along with the complete package. Okay. So according to some survey in US in 2017, so they predicted and market size of $1.5 billion. So now they are predicting much more into 2025. They predicted around $10 billion market feasibility of this energy harvesting. So there are different areas where it can be applied. Like one is consumer electronics. You can see this kind of this remote, this Philips remote. They come out with a completely battery-free remote, and it has application in healthcare. So this is from MIT. So they successfully tested this energy harvester for pacemaker. So this is heart of a pig. They tested on this. From heartbeats itself, they were able to harvest energy and they supplied that energy to the battery of the pacemaker. So there is no need to change the battery of pacemaker every 5 or 10 years. So for some patient, like if they cross the age beyond 60, 65, doctor doesn't suggest for the surgery, then replacing battery will be very difficult. So this can be one-time solution. Make replace just put the pacemaker along with the harvester. So battery life will be increased. Similarly, wearable harvesters, we can see this wristwatch. It works on temperature. That was talking about TEG, temperature difference between our skin and environment. Due to that, we can harvest the energy. Also, we have variables. I think okay. There is one more thing.
Professor.
Now they came out with variable shirts. Yeah,
Yeah, we can take another 5 minutes or so.
yeah. That I think this is my last one more, two
Okay.
more slides.
Okay.
And if you want to different resources, we can visit these things. ES Dialogue in Poland, NIPS Laboratory in Italy, or EPSRC network in Southampton University, UK, Energy Harvesting Society of USA, and in India, IIT Madras, IIT Kanpur, IIC. So many people are working on this energy harvesting. You can reach out. You can check these websites if you want to have more details. Coming out in summary, we have still challenge in the initial slides. We have seen that what are the different ambient sources and how much power is available there, but how much we can harvest is given here. So hardly we are able to get 10% of the available power. That is means only efficiency is only 10 to 15%. So that is a challenge. We need to design new harvesters. We have to come up with new materials so that we can increase this efficiency of these harvesters. So these are the challenges that we need to address: low cost energy harvesters and power optimization. We need management of power management and storage. So these all will make our life simpler and easier and good for the IoT applications. So there are different harvesters are like given one comparison here: vibration and thermal. We can decide, like, depends, again I say it depends on the application. We can decide whether to go for vibration or thermal. These are the challenges that we need to meet. So some of the references. So I would like to thank my collaborators and sponsors. These are the students, my students. I use some of their work during my presentation here. So thank you. You can contact me for any questions. Maybe you can ask a question here. I also can mail me your queries.
Thank you, Professor Pradeep. Maybe you can unshare so that we can see you. You can stop sharing, Professor Pradeep.
Yes. Yeah.
Yeah. Okay, your video is not coming. Thank you for this enlightening talk, Professor
Thank you.
Pradeep.
Thank you. Yeah.
Yeah. Yeah, your video is.
I'm not sure, but okay.
Yeah, it's coming now. Sure. Thank you. So, participants have asked few questions. I will read out for you.
Sure.
Uh, can the how can the damping factor affect the energy harvester?
Yeah, damping factor will affect the energy harvester. Like More the damping, like actually energy harvesting induce the damping in the system, and damping factor also will reduce the energy harvest output of the system. We cannot say that in case of electromagnetic energy harvester, if you are using it, it is also taking energy out of the system. In braking system, it has a lot of friction coming to picture. So there is way we need to look out for the optimization. How much has to be taken, energy has to be taken from it. So state answer is damping will reduce the output of the system.
Thank you, Professor. Uh, this, this question you might have answered in your slides. What is the future of energy harvesters?
Yeah, that's what there is a lot of a lot of startups coming now. Like if you visit, there are something you can I can just share that there is one lot of companies. One is Mouser in Bangalore. They're coming with most of the products with energy harvesters. And there is Mouser and there is Atmos. There are many startups in Europe and USA. But India, I have not seen any startup. But Schaeffler, German-based bearing manufacturer, they started working on this. Uh, they claim that they have one project with some government sector. They're trying it, but still, I have not seen any uh, uh, commercial application in India specifically. But there are a lot of startups in US and UK. So application, like I have already listed, there are a lot of applications.
Sure. Thank you. So, can the harvesters of different materials be coupled together?
Harvesters of different materials. Okay, I think at the end I have shown that is hybrid harvesting. Like now
Yes.
people are also thinking on this. I have shown electromagnetic and piezoelectric, but there is also option of combining solar as well as vibration energy harvesting. But again, energy management plays a crucial role there. So where we'll be needing help of electrical expert.
Okay. The connected question to that probably is it possible to have kind of a mini grid of such kind of micro powers wherein you have piezoelectric, photovoltaic, thermoelectric harvesters contributing to the energy supply?
Yeah, yes, exactly. Like recently, I have seen some researchers they have come out with this, like what you exactly photovoltaic as well as piezoelectric and thermoelectric. They are connecting it to a grid and microcontroller with microcontroller. It is possible, but thing is that if reverse flow happens, how it affects? Like usually the output from photovoltaic is more than piezoelectric. So controlling those things is crucial.
But these things are coming up, you mean, like
Yeah, now
capacity? Yes.
research point of view, they already shown that this is possible. But application point of view, we have not seen combination of these piezoelectric and different thermal and vibration combination. Still, we have not seen. But maybe, but I think in case of that remote control, I have shown. So it is combination of both vibration plus solar.
This question is from me. You have this shown the electromagnetic harvester. So in that pendulum, there are two magnets. You in the experimental setup, you have shown the two magnets, and there is a pendulum. So the question is like the base magnets, can it be displaced by some means? The displacement is given to the base magnet so that you can get an attenuation of that and the
Mhm.
displacement of the pendulum.
My system, you are talking about pendulums, right? So
Yeah.
yeah, in that case, at the end I have pendulums, and this excitation is given to the pendulums. Like it's a base excitation case. So they will be like if you are telling excitation to the magnets, so that is kind of giving initial conditions.
Yes. If you
Is it?
excite the base of the magnet also and excite the base of the pendulum
Yeah, yeah,
also,
that's it. Like
can
I
can
think
we alternate?
yes, yes. So that's what condition like we dynamics point of view we say giving some initial conditions. So
Mhm.
I think one of the graph I have shown that if you give some initial condition during that chaotic oscillations, so we can expect high cycle energy. Like it will oscillate in uh, at the higher amplitude, and we can expect more power from that. So, but that zone, that set of conditions, we need to identify. So, all initial condition, like we have to give some amplitude or we have to give some velocity. So, all the amplitude may not lead to the high power. Even they can be, that can be reverse effect also. It can lead to the minimum amplitude also. So, we need to identify in which initial condition zone it gives the better power. That is possible. We can give the initial condition, and for that again we need some control system, electrical control, and we can excite it by using some electrical part. I can have one more coil at the bottom,
Mhm.
and that can be reversed. So we'll be giving input to the coil, and it can excite the magnet.
Thank you, Professor Pradeep. I think those are the questions. Uh, I thank you formally now for the this session that you have conducted online. So, we would like to thank the speaker, Professor Pradeep, for
Thank
this Trees Talk 16, and we also like to thank the audience for their questions and this session. Thank you, and wish you a nice day ahead.
thank you. Anuj.
Thank you, Professor. Please visit IIT Dharwad
Sure, sure,
and let me know so that we can arrange your talk in person here next time.
sure. We can plan. Like also, we are planning for one talk from your side,
Sure.
so that we can make awareness of. I think you have a lot of support for students as well as faculty. So I
Yes,
think
yes, we have this correct. We want to travel to that part and then also talk about this support. We
yes,
have this Catalyze Tech program and also an incubation support. Now, in this next 15-20 days, we are going to come up with some incubation support. So, if you want to incubate some of your technology, you can incubate at the center. We will support you with some seed grant.
sure. That will be good for students and
Yes, yes, sure. Thank
thank
you,
you.
Professor. Thank you. See you then
Thank you.
next.
See you. Bye.